Good day, guys, and welcome to this class. In this class, we are going to be talking about GAUSS law. So, first, before we talk about GAUSS law, we must first understand the concept of electric flux, right? Yes, we must first understand the concept of electric flux. Are you getting it now? Remember that in the previous class, we talked about point charges. Are you getting it now? Yes, we talked about point charges from Coulomb's law. But to use GAUSS law, first we will imagine a field. In a surface. We imagine a field passing through a surface. Are you getting it now? Yes. And how do we measure that field? We measure that field by using. Are you getting it now? Yes. We measure that field by using what we call a flux, right? Now, what is electric flux? That is the first thing we are about to define now. An electric flux, because this is the fundamental of GAUSS law. First, we'll define electric flux. So, what is electric flux? Electric flux is defined as the number. You should write this down. Electric flux is defined, right, as the number of electric field lines that passes through a given surface. So electric field is defined as the number of electric field line passing through a given surface. Let's imagine a surface like this now, right? Let's say we have a surface like this. So we imagine that there are field passing through this surface. We imagine that there is an electric field passing through this surface, and this electric field, we denote them by using line convention. True or false? Yes, we denote them by using lines. Are you getting it now? So these lines, or these lines of electric field that is passing through this surface is called electric flux, and the symbol for flux is given as phi. Are you getting it now? Yes. The symbol for flux is given as what? Phi. So we can recap, right? That electric flux, is the number of feed lines. The number of what? Feed lines. So that means electric flux is equal to feed lines. And what is feed lines? What is feed? Talking about intensity, right? So that is E passing through a given surface. That surface talking about what? Area. A. So that means that electric flux can be calculated by the formula E, that is feed times the area. Are we getting it now? Yes. Now, this flux, as you can see, is perpendicular to the surface. If we zoom into this place now, let's say we make this one to be flat, right? Let's say we made it flat here. Then we begin to project lines. The same thing, we see electric field coming out, you need to make it straight as possible so that you can get the idea and the logic behind it. So something like this. Note. Okay. So it's making an angle 90 degree to the surface, right? Angle 90 degree to the surface. So what does it mean? It means that the flux, are you getting it now? is measured perpendicular to the surface. But what if the flux is not perpendicular to the surface? What if it is at an angle? Then we can say that the flux should be equal to EA cos, right, the theta of the angle. We are going to be looking into these concepts very soon. Now, let's take three case study. Yeah, we're going to take three case study and go wider into these concepts, right? Yeah, so we have understood the concept of electric flux, right? Yes, it's like measuring the field that is passing through a given surface. So to measure this field, we quantify it as electric flux. And we know that electric flux, as we have just said, is given by intensity times area, right? So let's take three case. Let's take three case study of how these flux move. Case one, let's observe when the flux is perpendicular to the normal of the surface. But listen, how do we come about normal? We said that on a normal condition, right? On a normally, are we getting it now? We said that on a normal condition, that the electric flux, right, is perpendicular to a surface. Are we getting it now? On a normal, let's just take one line. It says on a normal condition, the electric flux is supposed to be perpendicular to the surface. Now, let's take a surface now, and we don't know the direction that the electric flux is going through. So what do? We still represent this normal ID direction that this flux is supposed to pass. We still represent it. Are you getting it now? Yes, and pass a feed through it. I know the concept is somehow for you to grasp once, but as we begin to explain further, you will see. So case one, I get it now. Let's define a normal. Let's define a normal. Let's define a normal. Yeah. This is N, right? At an angle, I get it now, perpendicular to the surface. Now listen very carefully. Let's take our first case. If this feed, I get it now. If this feed is passing through the normal, yeah, it's passing through like this, like this, like this. Are you getting it now? We are going to measure our feed angle theta. Are you getting it? Theta is going to be measured. Are you getting it now? Yes, theta is going to be measured as the angle between these feed lines and this normal we define. Now, if you observe, they are parallel, so there is no angle between them. So that becomes what? 0. Are you getting it now? Now, recall that electric flux, is equal to electric field intensity times area cos theta, right? So this will give us EA cos 0, and this will become EA. So it means that it is maximum when the field is parallel to the normal of the surface. Electric field is maximum if, I get it now? Yes, electric flux, is maximum if the field lines are parallel to the normal of the surface. I repeat, electric flux is maximum if the feed lines are parallel to the normal of the surface. If that is correct, that implies that now we just made this surface to what direction? We just made this normal to the x direction, right? Yes, we made this normal to the x direction. What if we face this normal to the y direction? Like we rotate everything here to the y direction. How will it look like? If we do that, let's see. Make sure you note down case 1. If we do that, we'll call it case 2. Oh, sorry. We'll call that case 2. Call it case 2. So in this case right now, right, the feed lines is normal. So the normal of the surface is facing the y-axis. Are you getting it now? Is facing the y-axis. Are you getting it? Now let's pass an electric field through the surface. Remember that we are in case 2 right now. Hallelujah. So in here, we are passing an electric field here, passing it here, passing it here, passing it here, passing it here, right? Now, what is the angle between the feed and the normal? The angle between the feed and this normal is a perpendicular, right? It's perpendicular. That is angle 90. So when we go back to our equation, we can say that A, which is equal to flux, cos the angle theta, that is our angle is what? 90, cos 90. Remember that if you press your calculator, cos 90 is equal to 0. True or false? So everything here will be equal to 0. So it means that electric, are you getting it now? Flux is minimum, like it is 0. It is the most minimum. It is nothing when the field is perpendicular to the normal of the surface. Are you getting it now? When the field is perpendicular to the normal of the surface. If that is true, let's go to case 3. In case 3, are you getting it now? In case 3, here, we'll make it to, let's say, the z direction. So we take the normal to the z direction, if we like, or we can just make it to any direction. So if you want to make it to the z direction, right? So we can just turn it to the z direction here, or we can just say any direction, but we must define it in a physics identity. So where would the normal be? Remember that the normal is always at an angle, right? So the normal to this surface now will be like this, right? Yes, this is the normal to the surface. Let's pass an electric flux through this surface now. Let's see how it goes. If we pass electric flux through the surface, passing an electric flux through the surface, right? We discover that the angle made to the normal is angle theta. And we cannot define this angle. True or false? Yes, because we don't know the value. So in this case now, our flux is equal to A cos theta. Are you getting it? Yes. If this is true, we have successfully defined the electric flux. Let's continue our class. On the next session, we are going to be talking about some things you need to note down. Are you getting it? You must note it down in case of theoretical exam. The first question here is that there is no excess charge. Are you getting it? Make sure you write it down. There is no excess charge at any point on a conductor, the excess charge must reside at the surface. So inside the conductor, cannot find excess charge at one point. You say that this charge is more in this point. No, it's always at the surface. It's always at the surface of this conductor. So it's always at the surface. This is the conductor. So you can say there's excess charge residing here. No, it's always at the surface, right? Now, number two is that this total flux, I get it now, through a surface depend on the amount of charge. Make sure you write that down. The total flux through a surface is dependent on the amount of charge, I get it now, enclosed by the surface. So let's take a surface here. The total flux, that is electric field lines, we have already said passing through our area, depend on the amount of charge Q that is in this surface. So the charge here will determine the number of flux. Are you getting it now? Yes, that is in this surface. And the last thing to know is that I think that's all we need to know here. Now let's define Gauss law. Now, what is Gauss law? What is Gauss law? What is Gauss law? Gauss law, are you getting it now? State that the total electric flux through an enclosed surface is equal to the net charge. Are you getting it now? Inside the surface divided by the permittivity. Ah, my God. He said that the total electric flux through a surface is equal to the net charge, that is the charge enclosed by the surface, charge enclosed, divided by the permittivity. If you can know this, then you have known Gauss law. Are you getting it now? Yes. So in this case now, recall that this guy here is equal to E, right? A. But what of for an elemental area? For an elemental area, say something like this, we have an elemental area, dA, and we want to integrate over the surface. So that means that this is equal to the integral, right? The integral of the enclosed surface. This means enclosed, but just know it's integral. E dot dA, right? Are you getting it now? Yeah. So from here we can equate. That implies that E times A is equal to Q En all over the permittivity. Is that, are we getting it now? You are getting it right? Yes. Alright, so if this is true, let's see how we can apply Gauss law to charge distribution. Let's see how we can apply Gauss law to charge distribution. It's just as easy as this. It's very easy. Just as easy as this. Are we getting it now? Yes. So first, let's apply Gauss law to point charge. We'll be applying Gauss law right now to point charges. Application of Gauss law to point charge. Don't worry, that will be covered in the next class. I don't want this class to be more than 20 minutes. So in the next class, we are going to be solving all the examples, I get it, and the application of Gauss law. Then after the next class, in the other class, we will talk about the exercises. And after that, we move to chapter 4. Remember, are you getting it now? That each videos is segmented. Are you getting it? Please make sure you like, subscribe, share to your class, your friends, and loved ones. If you also need a private tutorial, you can also DM me on my WhatsApp number. God bless you. Thank you.